Welcome to a discussion of what makes the CAN protocol, implemented in WaterCAN, ClusterCAN, and CCAN, so valuable when developing distributed and cloud-based applications. At the end, we will make the CAN protocol face off against the Chaos Monkey, a tool popularized by Netflix after an AWS failure took down almost every AWS service except Netflix. But first, let us discuss the CAN protocol's basic nature. We begin with an example. Consider this event receiving method, written in Java, found in the publisher object of the PubShare publication subscription system. This method, which accepts a single string, that is a new event, is the entry point through which a person submits events to a topic. As you can see, the method has only 3 lines of code. In the first line, the instance variable storing the most recent event is updated, so that the next time the human publisher asks where he left off, he will see the correct entry. In the second line, the publish object sends a message to the topic to add this event along with some auditing information. And in the third line, we simply send back an acknowledgement to the sender so he knows the submission was successful. Now, if this were a sequential program running on a single CPU, nothing very interesting could go wrong here. If the system crashed, the topic object and the publisher object and the sender of the event would all go away at the same time, and there wouldn't be much opportunity for errors and inconsistencies to arise. But suppose this application is running on a cluster and the topic object is on a different node from the publisher object. First of all, this code probably couldn't survive any node crashes at all because there is no explicit checkpointing code. But suppose we are running on a framework that has transparent checkpointing. Even then, we are still in trouble. Suppose the add event message is sent before the checkpoint, and suppose a crash occurs before the checkpoint is complete, causing a restart from the previous checkpoint. Then this method will be rerun from the beginning. The add event message will be sent a second time, and the event will be duplicated in the topic. Or suppose that the add event message is sent and the publisher gets back the acknowledgement from the topic before the topic checkpoints, but the topic node crashes before its checkpoint finishes. Now the publisher thinks that the topic node has the event, but the topic has lost it, and the event is gone. Finally, suppose 2 events come into the publisher at almost the same time, and suppose the framework implicitly spawns multiple threads to handle the multiple incoming messages, the way Java RMI and Corba do. Then the 2 message threads can interlace in such a way that one event is stored in the last event instance, while the other message is actually the last event submitted to the topic. Depending on how you interleave the checkpoints and the messages and the acknowledgements, there are hosts of other sequences of node and network failures that can lead to duplication, loss, and inconsistency. We have merely looked at 3 examples. The code to handle all the failure modes could easily be an order of magnitude greater than the 3 lines of code needed to do the actual work. With ClusterCAN as the underlying development framework, only the 3 lines of code required to do the actual event are needed. The protocol is a little bit too complicated to explain in this video, but basically the message to the topic and the acknowledgement to the publisher are held until after a transparent checkpoint of both state and message at the end of the method. The message has a unique ID embedded, so if a network failure or a node failure causes the framework to be unsure if the add event message was processed by the topic, the framework resends the message with the same ID. If the topic has already processed the message with that ID, instead of processing the message a second time, it simply returns the result computed the first time. The result of the CAN protocol's operations is that we get exactly once message processing and guaranteed consistent output validity regardless of what network and node failures may occur, regardless of the ordering of those failures. Writing reliably correct code on top of a CAN protocol framework is often quite similar to writing sequential code for a single node. So what happens when the CAN protocol runs up against the chaos monkey? The chaos monkey randomly zaps nodes in order to test the cloud application's robustness in the face of partial cluster failures. In fact, we had built and used chaos monkeys to test the CAN protocol apps long before the term chaos monkey was popularized. The chaos monkey can slow a CAN system down, but any of the parts of the application that can continue to compute do continue. And we have never seen an inconsistency or a data corruption in a CAN-based application caused by a chaos monkey invoked failure. So what happens when the CAN protocol faces off against the chaos monkey in a SmackDown? CAN emerges victorious. Thank you.